let's fix a positive number s among all positive x and y with sum equal to s. When is the product x times y maximized and what is its maximum value? This can be solved using calculus, but we're going to do it with elementary math. You don't need to know anything, okay? It's going to be basic math, basic algebra. We're going to answer this question and give a beautiful geometric interpretation. It's deeper than it looks, okay? So let's just dive right into it and first understand what we're trying to do. So we've got a positive number s, and we're looking at all the positive numbers x and y. These are real numbers. They need not be integers or whole numbers, but x plus y is equal to s. Okay, all of the possibilities where x plus y equals s, and we want to figure out when the product x times y is maximized. So interested in the product x times y. Now the first thing we want to do with this kind of problem is just put everything in terms of one variable. Okay, so we've got x plus y equals s, so we know that y is determined by x. Once you know x, there's only one value of y, that is s minus x. Okay, so we can write it out as follows. So therefore y is equal to s minus x if you subtract x from both sides. So the product we're interested in, x times y, is going to be x times s minus x. And we're interested in when this is maximized. Now it's natural to think about this, when x is really small, s minus x is large, so there's a trade-off. If s minus x is large, perhaps the product would be large. But of course, if x is small, that would eat away into the product and make it small. So they kind of have to be balanced. And you already can intuitively see something, that perhaps it's balanced when x is right in between 0 and s. Okay, so that's the intuition. That's always helpful when thinking about these problems, is right between 0 and s, looking at the closed interval 0s, right at the midpoint. Okay, right at the midpoint, that could be when there is a maximum. But we don't know that yet, and we want to make sure that our answer is correct. So how do we do that? So the first thing is you write out this x times s minus x. Let's write it out. It's going to be sx minus x squared. So remember here our variable, our x is our variable and our s is a constant that's fixed at the beginning of the problem. And what we can do is we can do some quick quirky tricks to this to actually make it seem obvious about what this actually is. Okay, so it looks a little bit opaque at the moment, but what we can do is we can do this trick, which I'll show you, is we take minus of x squared minus sx, okay, first of all. So just taking out that minus sign and put it as x squared minus sx, which is minus x squared plus sx, okay, so nothing there. Now we're going to complete the square, okay, so completing the square basically means the following, and it's a quick review of completing the square. We want to write this as x minus k squared, okay, so for some constant k, which we don't know yet, we want to write it as x minus k squared. Why? Because remember when you use the binomial theorem, x minus k squared is x squared minus 2kx plus k squared. Okay, now there's an issue here. Okay, we can get the x squared minus 2kx to match up with the x squared minus sx, but the k squared term is excess. So we're going to have to subtract that off, and I'll explain what I mean. So I'm going to write it here. We're just going to choose, first of all, we want our k to be s over 2. Okay, so if we want our 2k to match up with negative 2k to match up with negative s, so therefore s has to equal to 2k, and so therefore k has to equal to s over 2. That's all well and good, that's quite nice. So we're going to get minus of, we're going to write this as x minus s over 2 squared. Okay, now x minus s over 2 squared, your k squared term will be there. And your k is equal to s over 2. So that's s over 2 squared. So we're going to have to subtract off that s over 2 squared to get the same expression as x squared minus sx. Because x minus s over 2 squared will be x squared minus sx plus s over 2 squared. So by subtracting off the s over 2 squared, we're going to get just x squared minus sx. And why this is so cool is this is now going to be, by just distributing the minus signs, we're going to get s over 2 squared minus x minus s over 2 squared. Okay, and now we're going to get somewhere. So if you're loving my content so far, we're going to do the big reveal now. Please don't forget to smash that like button and subscribe for lots more fun math content. It really helps grow the channel and help as many people as possible. This is infinite, free, accessible math education. Clicking that like button is free too, and dropping your comments down below means the world to me. I love reading all comments and engaging with you. So now we've got that expression there, so that's our expression. I'm just going to write it here. Our expression now, we can say sx minus x squared, which is the quantity we wanted to maximize, right? That was x times y at the beginning. that's going to equal to s squared over 4, which is s over 2 squared, minus of x minus s over 2 squared. Now this process is called completing the square. What does it tell us? Well, we know that this quantity x minus s over 2 squared is always a non-negative number. It is a perfect square. A negative of that is always going to be a negative number or a non-positive number. Could be 0. Okay, so this whole quantity here is going to be less than or equal to 0. So the time when this whole expression is maximum is when this quantity here is exactly 0, right? That's the time when it's maximum. Otherwise, you're subtracting off some number, which is positive because it's a perfect square. So therefore, you want this quantity to be 0 is exactly when x is s over 2. Okay, so maximum, so I'm going to say it's maximized when x is equal to s over 2. That's what we predicted at the beginning, but don't forget to watch a bit more because I'm going to show you some beautiful interpretations, geometric interpretation, and also a calculus interpretation for this. So when x is equal to s over 2, it's maximized, and the maximum value is equal to s squared over 4. Okay, that's what it's going to be. So the max value is just going to equal to s squared over 4. And now we are at a good point. Okay, we've solved the problem. Okay, we know that that's the solution to the problem, but what's actually going on geometrically? So here's the first observation. The first observation is that this s squared over 4 minus x minus s over 2 squared, what it actually looks like is it looks like a parabola. Okay, so if you graph it on the xy axis, xy plane, it looks like a parabola. We're looking at x and y not positive numbers and they add up to s. So we're kind of looking at this range from 0 to s, and you sort of see here that when it's s over 2, its maximum value is going to be s squared over 4, and you get this parabola which is inverted here. Okay, that's your parabola there, and that's sort of the graphical presentation of what's going on. Okay, so your product is optimized, its maximum just at the middle. Okay, just at the middle, s over 2. But what actually this problem is representing is saying that x plus y is s. Is another way of saying it is that 2x plus 2y is equal to 2s, and 2x plus 2y is none other than the perimeter of a rectangle with side lengths x and y. So among all rectangles whose perimeter is equal to 2s, when is the area of the rectangle x times y maximized? When is that maximized? That's when both the sides of the rectangle are equal to s over 2. X is s over 2 and y is s over 2 because they add up to s. And that's when it's maximized, that's when the rectangle is a square. So among all rectangles with a fixed perimeter, 2s, the area is maximized when the rectangle is a square. Pretty cool, right? That's a pretty cool geometric interpretation. But let's now solve this with calculus as well, just to give you a beautiful and simple explanation so you can compare the different methods. So with calculus, the function we wanted to maximize is f of x is equal to x times s minus x. Remember the original function we have, and you have this function which is now equal to sx minus x squared. Now this function is defined on the open interval 0s. Okay, you could sort of say closed interval as well if you're just saying that the numbers are non-negative, but it won't matter. Okay, so we're defining this function here. We want to find its maximum value if it exists, which we don't know. The way we do it in calculus is we take its derivative. So f prime of x, the derivative is going to be s minus 2x. So you're going to get s minus 2x over there. And now you just want to understand the sign of the derivative. Okay, so you do a sign chart for the derivative. The derivative is positive, s minus 2x. So if you think about it, this is positive precisely when, if you add 2x to both sides, it's when s over 2 is greater than x. Okay, x is less than s over 2. And the derivative f prime of x equals to s minus 2x is negative precisely when x is greater than s over 2. Okay, so the function, the derivative is positive when the function's increasing, and the derivative is negative when the function's decreasing. Something we saw when we had the parabola. So when you had the parabola, you can sort of see, so f prime, the sign chart, f prime greater than 0 on the interval 0 s over 2, and f prime is less than 0 on the interval s over 2s, and the critical point when f prime is equal to 0 is just at s over 2. Okay, at x equals to s over 2, and that's very evident just from the graph, and that's how you do it in calculus, because you see there's a sign change, the function's increasing until s over 2, decreasing after, it has a single critical point, therefore that has to be a max. You don't even have to check the endpoints. You don't even have to check the endpoints, so it's clear in this case that it's 0 at the endpoints. You don't have to check the endpoints because you know that there's only one critical point. Okay, so drop a comment down below. What's the explanation for that? If you have a function, let's say, defined on the real numbers, and it has one critical point, why is it true that that has to be either a max or a min, global max or global min? Why is that true? Why don't we have to check the endpoints of if it's defined on an interval? So I hope you loved that video, and I've got 2 fun videos for you to really practice with calculus ideas and more. The first video is how to graph this function. It's a very beautiful step-by-step graphing process using calculus, using critical points, inflection points, concavity, limit to L'Hopital's rule, and so many ideas all in one video. How cool is that to really master? Check out that video here. And another fun video you're going to love, it's a little bit different from this video, but it's quite related. A beautiful proof of why the area of a circle with radius r is pi r squared. Okay, so this is the first principles proof, and probably you haven't seen it before. It's very aligned on a single limit. You're gonna love this video. Okay, check it out here. Wish you an amazing day.